So, good morning everyone. My name is Amit Kumar. So, today we will be discussing about the linear regression and its assumption. So, linear regression it was initially introduced by Francis Galton in late 1800s when he was finding the relationship between the height of the parents as well as their children. So, this was the first time when he used it, linear regression. So, linear regression basically it is a statistical technique which shows the relationship between the dependent as well as the independent variables. So in this lecture, what we will do is that I will not only explain the theoretical part, but also at the same time, what I will do is that I will take a real-time data and I will run all the important necessary assumptions on that data, and I will show how those assumptions work in the real-time data. So basically, as I have said earlier, that linear regression it is a statistical technique which shows us the relationship between the dependent as well as the independent variables. So mathematically, it can be written as y is equal to alpha 1, alpha plus beta 1 x1 plus say beta 2 x2 plus some error term. So here x1 as well as x2 are known as the independent variables. Independent variables, which shows it impacts on the dependent variable, that is y. So here y is known as the dependent variable. Dependent variable. E is the error term, which is also known as the residual part. And beta 1 as well as the beta 2 part is known as the parameters. Parameters. Well, alpha is the constant part, constant term. So mathematically, this is how a linear regression model it represent as. So let us explain. Let me explain this topic using a real-time data. So what I have done is that I have taken this table 1.1 from Jeffrey Woolbridge book. So in this table 1.1, we can see that the first column it consists of the observations. So the total number of observations is about 526. So the first variable, that is the dependent variable, is the wage, followed by the independent variable education, experience, female, as well as the married. So if a person is female, then it is coded as 1, or else it is coded as 0. Similarly, if a person is married, then it is coded as 1, or else it is coded as 0. So these both are known, these both variables are, since it is a qualitative in nature, it is known as dummy variables. While variables such as say education, wage, education, as well as experience are continuous in nature. So we are having both qualitative as well as quantitative data in our data. So now if we write here wage as the dependent variable, alpha plus some say beta 1 into education part and beta 2 into experience part plus beta 3 into female plus beta 4 into married and some error term. Now here we can say that education, experience, female, as well as person is married or not, all these variables are independent variables, and it shows its impact on the dependent variable, that is wage. So this is the dependent variable. So what we can see here is that there are two things which are supposed to keep, which we are supposed to keep in mind, is that the direction. So the direction part, that is whether whether the impact of a particular independent variable is positive or negative, it is shown by this symbol plus or minus. Let's say if education is directly correlated to wage, so if education of a particular person is increases, so if we plot say education on the x-axis and wages on the y-axis, so we know that as the education of a particular person it gets increased, obviously the wage also it will get increased. So there is a positive correlation between both of these variables. So we can say that there is positive. So here it is related, denoted by the positive sign. Similarly, the second thing is the magnitude part. So this regression it also tells us about the magnitude, that is how much is the impact of education on the wages. That is basically represented by this beta 1 part. So let's say if this beta 1 part is 0.9, okay. So if we change 1 unit of education, then there will be 0.9 unit of change in wages. So we can see how much strongly there is a correlation between education as well as wage. Similarly, if experience if we take experience and if we find run the regression, and if we find that the value of beta 2 is say something around say 0.01, say, we can say that as the experience of a particular person increases by 1 unit, then his or her wages increases by 0.01 unit. So that is very much less in magnitude. So the linear regression, it says us about two different things. The first one is the direction part, whether it is positive or negative, and the second part is the magnitude, whether how strong or how much strong the impact of this independent variable is on this dependent variable. So this is what is defined by this linear regression thing. So now coming to the assumptions of linear regression. So basically there are more than six or say seven or eight assumptions of linear regression, but here in this class we will fundamentally discuss only six very important assumptions of linear regression. So the first one is that the variables whichever we are taking, it should be exogeneity in nature. So basically what it tells us is that our independent variable, it should not be endogenous in nature. So we will be discussing this in the next slide. So now the second assumption is that there should be a linear relationship between the dependent as well as the independent variables. The third one is that whatever data we are taking, there should be no multicollinearity problem in our data. The fourth, fifth, sixth assumptions are dependent on the residual part. It is also known as the error part. So the fourth assumption is that our residuals, whichever we are taking, it should be normally distributed. So whenever we plot, the residuals of our data, most of our data, it should lie in and around say this mu values. Mu is equal to 0, and 68% of our data should lie in between this mean value itself. Coming to the fifth assumption, we should have a homoscedasticity thing in our data. So homo means basically equal, and skedasticity means variance. So skedasticity means variance. So the variance of our errors, it should be equally distributed. Coming to the sixth assumption, that there should be no autocorrelation in our data. So now what I will be doing is that I will explain each assumption individually, and at the same time, as I have said earlier, that I will also take the real-time data and I will run all these assumptions on that particular data, and I will show whether how these things it shows in real-time data. So coming to the exogeneity part. So let us understand what exactly exogeneity and endogenous thing is there. So if we take income on say income as an independent variable, so alpha says beta 1 plus some education. So let us take this equation wherein the income of a particular person, it is dependent on the education of that particular person. This is what basically this mathematical equation says. So diagrammatically we can say, as the education of a particular person increases, obviously the income is also get increased. So this is what a basic so normal notion of any particular model of income. Now we also know that education, whenever a person is pursuing higher education, let's say a person is willing to study MS in US. So definitely that particular person, he or she, he must be having say 40 to 50 lakhs Indian rupees in order to pursue higher education in foreign countries. So what here we find is that the education, it is interdependent on the income. So here the education, it's no longer an independent variable. So it is dependent on the dependent variable also. So this kind of variable, it is known as the endogenous variable, which is not desirable in our data. So what we should do whenever we find that our particular data is having endogenous variable, definitely we should not take this kind of variable. What we should do is that we should take some other variable which is known as the instrument variable. So instead of taking education, we should take some other variable, and we should find whether our data is having endogenous problem or not. So only if our variable is endogenous in nature, only then we can run our linear regression. And if any of this assumption it is violated, then what will happen is that our data, our result will be biased as well as inconsistent in nature. So this is what we will face if our if our data violates any of these six assumptions. Now coming to the next assumption, that our data, whichever we are taking, it should have linear relationship between independent as well as the dependent variable. So what I will do is that I will initially show you the data which I have taken. So this is the data basically. So this is the data wherein target is the dependent variable, and feature 1, 2, 3, all these three are the independent variables. So what we are doing is that we are finding the impact of all these three, feature 1, 2, 3, on target variable. So this is the data. What I have done is that I have taken the data. I am using Jupyter notebook. I have run. I am In order to find all this relationship. What I have done is that using the Python, I am trying to establish a relationship between the feature, the dependent as well as the independent variables. So now coming back to the theoretical part. So I have said that there should be a linear relationship between say dependent as well as the independent variable. So initially I will show it using the diagram, and then I will later jump onto the mathematical part. So here figure shown in the figure A as well as B, there we can see that there is a linear relationship. So in figure A we can see as the value of x increases, obviously the value of y also it get increased. So let's say on x axis we have taken education. So on y-axis we have taken income of a particular person. So what we assume that as the education of a particular person increases, obviously the wage or the income of that particular person also get increased. So here we find a positive correlation in figure A between the education as well as the parameter y, that is income. Similarly in figure B, here we can see that there is a negative correlation as the value of this say the value of uh, say this on the y-axis I have plotted price, and on the x-axis I have plotted quantity demanded of a particular good. So here we can see when the price was P1, the quantity demand was Q1. As the price it got decreased to P2, what happened is that the quantity demand it got increased to Q2. So from Q1 to Q2, we got the quantity demand it got increased when the price it dropped. So here we can see that there is a negative relationship between both the price as well as the quantity demand of a good. Basically, it is linear in nature. In figure C, we can see that there is a non-linear relationship between both x as well as y variables. So here we can see that as the value of x increases, the value of y it increases exponentially. So it is in a kind of y is equal to e power x kind of relationship we are having in this kind of scenario in C. So mathematically, whenever we say linear in relationship, what we basically mean is that let us say we are having a equation y is equal to alpha plus beta 1 into x1 plus some error term. So this is first equation, y is equal to alpha plus beta 1 into x1 square plus some other term. This is second equation, y is equal to alpha plus beta 1 square plus x1 square plus some error term. This is third equation. So here in equation 1 as well as 2, it is known as linear in parameters. Now I will explain why it is known as linear in parameter, while this equation 3 is non-linear in parameter. Non-linear in parameter. Now, whenever we see this kind of equation 1 as well as equations 2, what we see is that the beta 1, that is the parameter part, it is having only the power of 1, that is beta 1. But in equation 2 we can see that the independent variable it is raised to the power of 2. It's okay. I mean, the equation should be linear in parameters, and at the same time it might be linear in variables or not. That is that is a different part. I mean, even if it is not linearly not related with the independent variable, still it will be known as the linear in parameter kind of model. Now in equation 3 we can see that this particular equation we are having beta 1 square. So in this kind of scenario, definitely we will say that this particular equation 3, it is non-linear in nature. So now what I will be doing is that I have taken this data as I have said earlier. So I will be checking whether our independent variable and dependent variable are linear in nature or not. So in this figure 1, figure this I have plotted, I have taken this, I will take this copy image. Okay. So what I have done is that I have plotted the relationship between feature 1 as well as the target variable in figure A. So I have found that there is a positive correlation between both of these variables. Similarly, in feature 2, we can see that there is some sort of relationship between feature 2 as well as feature target variable. In feature 3 also there is no clear-cut relationship and positive correlation between feature 1, feature 3 as well as the target variable, but still it's okay. I mean, we can say that there is some sort of positive correlation between both of these variables. Now coming to the next assumption, that is there should be no multicollinearity in our data. So now let me explain this using an example. So let us take a model wherein the price of a house is taken as a dependent variable, alpha plus beta 1 into area of that particular flat, and say beta 2 into say number of bedrooms for some error term. So this is one kind of model wherein the price of a house of a particular uh, locality, it has been predicted using the area of that house and also the number of bedrooms of that house. Now we know that uh, the interpretation of this could be uh, for a particular increase for a 1 unit increase in area, there will be beta 1 increase in the price of the particular house, keeping number of bedrooms constant. So this is what the basic assumption or basic interpretation of the linear regression is. So what we have assumed that for a unit change in area, there will be, let me write it here. So for unit 1 unit change in area, there will be beta 1 change in the price, keeping number of bedrooms constant. So this should be constant whenever we are making an interpretation like this. What we say is that this independent variable, it should be constant. Now imagine if this area, it is directly correlated with this particular variable, then what happens is that our assumption, it gets null and void, because what we have assumed that is that our independent variable, it should be constant. But if both of these are interrelated with each other, then definitely our assumption, our interpretation, it will there will be no meaning for it. So as the area, let's say area of a particular house and number of bedrooms. So we know that as the area, that is 1100 SFT, if I am taking, then it is 2 BHK, and for 1500 SFT, obviously the number of bedrooms, it will get increased, say it's about 3 BHK. So what we can say here is that as the area of a particular flat, it gets increased, obviously the number of bedrooms also, it gets increased. So we can see here that there is a positive correlation between both these variables, area as well as the number of bedrooms, so which is not desirable. Now how do we detect whether our data is having such kind of problem or not? So the detection method. So the first one is the calculation of variance inflation factor. So what we will do is that we will take the real-time data and then we will run the VIF on all these independent variables, and we will find whether the VIF of all the independent variables is greater than or less than 5. So if the VIF of a particular independent variable is greater than 5, then we can clearly say that that particular independent variable is having multicollinearity problem. Now this is the first method. Now the second method is by building the correlation matrix. Correlation matrix. I will be showing this in the the real-time application part also, how the correlation matrix is being built. So basically in correlation matrix, all these independent as well as the dependent variables relationship, it will be assessed, and we will check whether how much strongly the independent variables are related with each other. Now once we find whether our data, it is having multicollinearity problem, so what is the next procedure or next way in order to solution, what is the solution for it? So what we will do is that we will simply drop one of the variables. So we can, in this kind of particular model, what will be doing that we can drop this number of bedrooms variable, and then we can uh, you know we can run a new model, say price is equal to alpha plus beta into some area, some error term. So this is the new model wherein we have dropped the number of bedrooms variable. So in this way we can avoid our multicollinearity problem by dropping one of our variable. Now I will be showing the same thing in the real-time data. So now what I have done is that I have imported the variance inflation factor, say here, from say stat models. So these are the uh, these are the models which we use to verify what is the VIF of a particular independent variable. So here we can see the VIF of feature 1, 2, 3, it is somewhere around 1. So basically it is not beyond 5. So we can simply say that the data which I have taken, it is not having such kind of problem. Now the second way I have told you that we can even do this by visually checking whether how much is the relationship strong between all these independent variables. So here we can see that feature 1 as well as the feature 2, it is very weakly related with each other, since the correlation value of both of these feature 1 as well as feature 2, it is minus 0.001, which is very very much weakly correlated with each other. So we can simply say, we can see this correlation matrix and we can simply assess whether how much strongly or weakly our independent variables are related with each other. So now coming to the next assumption, that is normality of residuals. So what basically residuals is? So all these fourth, fifth as well as the sixth assumption, it is dependent on this residual part only. So here in this figure, this diagram, it is taken from the Jeffrey Woolridge book. So here in figure 2.4, we can see this is y. Let us say this is y1. This is the exact value of that particular observation. But my linear regression, what it did is that it predicted somewhere around here y1 hat. So now this y1 minus y1 hat is basically, it's a residual part, or we can even say it as a error term, which is, I mean, the less the error term, the good the accuracy of this particular model will be, obviously. So let us say this is y1. So this is error is equal to e1. Similarly, if we take this particular observation, which is denoted as v2 y2, and on the predicted value was y2 hat, so now this difference will be e2. So now what we will do is that we will calculate e1 comma e2 error so on till en, and then what we will do is that we'll plot all these errors using a KDE plot or quintile plot, QQ plots. Using these plots, what we will do is that we will try to plot, and we will we will see whether, check whether these particular errors are normally distributed or not. So if it is normally distributed, then definitely our data, our assumption, it will get satisfied. Now coming to the real-time data, what I have done is that I have taken the residual plot part, and then I have tried to plot it. I have found that there is this particular residuals, it is almost normally distributed, while we are just having a small bump here, but still it's okay. Similarly, we can, as I have said earlier, that we can also do it using the QQ plot. What I have done is that I have plotted the QQ plot, and here the thumb rule is that if all the data points, it lies very much close to this red line, then we can simply say that our the errors of our data, it is normally distributed. Now coming to the next assumption, that is the homoscedasticity part. So basically, homo means equal and skedasticity means variance. So homoscedasticity, it's quite a tongue twister for me. So homo means equal and skedasticity means variance or spread. So what is expected for our model to behave is like, there should be equal variance whenever we plot, say. So what we do is that we basically uh, plot a scatter plot between errors as well as the predicted value. So what basically is decide kind of scenario is that whenever the predicted value, whenever this x value it gets increased, the y value, it should be remain constant. So here we can see that as the value of the x increases, the variance, that is the spread from its mean value, it is almost constant. The value of a as well as the b, it is constant. So this is what is being depicted from this diagram A, wherein there is a situation of homoscedasticity. Now coming to the situation of figure B, here we can see as the value of y increases, x increases, obviously the value of y also it get increased. So say so here we can see as the value of x increases, obviously this value, this spread also it get increased. So this is a kind of situation wherein we will face a problem of heteroscedasticity, which is not desirable. Which is not desirable. So the same thing I have shown in this diagram also. So in figure 2.8, we can see there is homoscedasticity between the variable y. Say this is the variable y and this is x. We can see that the variance, it is almost equal. Even if we take the variable x1, x2, x3, the variance is equal. But the same is not seen in the figure 2.9, where we are having a situation of heteroscedasticity. In this when the education value was 16, the variance was very much high. Similarly, when it reached 12, the variance it got decreased, and when it was about 8, the variance it was very much less. So this is what is desirable. So this can also be, explained using another example. So what we will be doing is that we'll take an example wherein education will be in on x-axis and income will be plotted on the y-axis. So we will take a data like this. These are the data points, the observations of a particular person. So what I have done is that for this is a particular person A and this is a particular person B. Now we can see that despite the fact that this particular person A education it's almost equal to B, his or her income is more. So this is IA and this is IB. So here we can see that this particular person he might be working somewhere in software industry or he might be an investment banker, and this particular person B he might be teaching somewhere as an assistant professor in some university. So his education level might be PhD somewhere, something about PhD, but still his income is less when compared to that of A. So why is this happening? So this can be because of the fact that the particular person B, his tastes as well as his preference is different when compared to that of the person of A. So in this kind of scenario, we will face a problem of heteroscedastic kind of problem. So now let's check whether my data, real-time data, it is having such kind of problem or not. So what I have done is that I have plotted a scatter plot of the residual part with the error part, residual part with the predicted part, and I have found that there is no particular pattern, or what I have found is that the error it is almost equally distributed in my data. So basically, there is a homoscedasticity kind of situation in my data. So I don't have any heteroscedasticity kind of problem. Now coming to the next assumption, that is the autocorrelation part. So autocorrelation means the errors of the present errors if it gets correlated with the past errors. So if yt is equal to alpha plus beta 1 into yt minus 1 plus some error term e1. Similarly, yt is equal to alpha plus beta 2 into yt minus 2 plus some error term e2. Now, if error 1 is correlated with error 2, then we will basically face a situation of autocorrelation. And basically, this autocorrelation kind of problem we usually face this kind of situation in mostly in time series data only. So what we do is that if we plot plot the our errors, and if we get some sort of pattern like this, say like this. Now this is known as positive autocorrelation, which is not desirable in our data. So what we should have is that whenever we plot our data, errors of our data, we should have some irregular pattern. I mean there should be no particular pattern. It should be something like this zigzag. So this is basically it is known as negative autocorrelation, and this is what is desirable for our data. Now what I will be doing is that I will take the residual parts, and then I have plotted it on the real-time data. Now what I have found is that there is no particular pattern of the residuals in my data. So basically there is no autocorrelation kind of problem in my data. So to sum up, what we can say is that the first assumption of linear regression is that our data it should have exogenous variables in our data. The second one is that there should be linear relationship between the dependent as well as the independent variable. The third one is that there should be no multicollinearity kind of problem in my data. Coming to the fifth, sixth one, which is dependent on the residual parts. The fourth one is that the residual, whenever I plot it, it should be normally distributed. The fifth part is that there should be homoscedasticity kind of situation in our data, that is equal variance, and finally there should be no autocorrelation errors in my data in my data. So this is all about linear regression and its assumptions. So thank you everyone to give me this opportunity.